Hello and welcome to this video on using the definition of a basis to verify a given basis. Well, really, it's going to be more of determining if a set of vectors is a basis for a given vector space. Alright, but we're going to be using the definition of a basis a lot. Alright, so in this video I'm going to define what it means for a set of vectors to be a basis for a vector space, and then go over loads of examples, just with vectors in R2 and R3, right, two-dimensional and three-dimensional Euclidean space, so that if you wanted to, you could go to like a GeoGebra or Desmos and some graphing calculator website, or even draw it by hand. You could actually picture them. And whatever I apply here in these examples in R2 and R3 can be applied in higher dimensional Euclidean space, or even in general vector spaces, so like R4, R5, R6, or other examples of vector spaces that I'll get to in future videos. Alright, so let's begin. So here I have the definition of what it means for a set of vectors to be a basis for a vector space. Alright, so a subset S of a vector space V, meaning that S contains some vectors from V, it's a subset. Right? A subset S of a vector space V is a basis for V, or a basis of V, if S is a linearly independent spanning set of V. Now, I'm assuming you know what these terms mean by this time, right? Because if you've been watching videos I've been putting up, or you've seen other videos, or read some other texts, hoping you know what it means for a set of vectors to be linearly independent. And I'm also assuming that you know what it means for a set of vectors to be a spanning set of a vector space. And I might refresh your memory as we go through this video as well. So another way to put this definition of what it means to be a basis of a vector space is this. A set of vectors S is a basis of vector space V if the two following things are true. 1. S spans V. In other words, the span of set S is equal to V. That means that every vector in V can be written as a linear combination of vectors in S, right? That's what the span of S was, right? It's the collection of all linear combinations of vectors in S. And 2, you have to show both of these things, and 2, show that S is linearly independent. Now that meant that no vector in set S can be written or expressed as a linear combination of other vectors in set S. Or if you were to try to find a linear combination of vectors in S that made the zero vector, the only linear combination will be the trivial one, right, where all the scalars are zeros. You take 0 of vector 1 plus 0 of vector 2 plus 0 of all the vectors, and that's the only way to get the zero vector. That was another way to show that S was a set of linearly independent vectors. Alright, so that's what I'm going to be doing in all the examples I have. I have plenty of them in this video. I'm be showing both of these things. And if one of these fails, right, if this is false or if this is false, then S would be not considered a basis for the vector space V. Alright. So my first example, probably a simple one if you think about it, but so my instructions here for this and for all the examples in the rest of this video is going to be just simply to determine if the set S is a basis for vector space V. So my set S here is made up of the vectors 1, 0, 0, 1, and these are vectors from R2, right? We have a subset of R2 here. And the vector space V is the vector space, R2, the two-dimensional Euclidean space. All right, so I'm going to go through those two things we need to check. So 1 is, the span of S equal to R2, right? Or in other words, does S span R2? All right. Again, I've put up videos on this where we've tried to figure this stuff out. Figuring out if one set spans a vector space. So remember what this means. The question is, for every vector in R2, now remember what any vector in R2 would look like this. Say V equals, V1, V2. Every vector in R2 looks like this. So I have some general representation, an arbitrary vector in R2 here. For every vector in R2, represented by this here, V1, V2, can we find, say A1 and A2, these scalars, such that A1 times 1, 0 plus A2 times 0, 1 is equal to this vector V1, V2. Right. In other words, can I take any vector from R2 and write it as a linear combination of the vectors in S? All right, now again, I hope this one's obvious. If I just let A1 be V1 and A2 equal V2, then we're golden. So the answer to this question is yes, right? V1 times 1, 0 plus V2 times 0, 1 would be the vector V1, V2. So for any choice of V1 and V2, for any vector in R2, I can find a linear combination of vectors in S that make that. Now, the way I would normally look at this, or the way I've done in other videos, is remember this corresponds to a system of equations involving A1 and A2. Right? The variables are A1 and A2. What I'm trying to solve for are A1 and A2, not V1 and V2. V1 and V2 are just numbers I pick. These are fixed. Right? So this linear combination here corresponds to a system. Right? And this system would look like this. A system of linear equations where, the first components I'd have A1 plus, 0 A2 equals V1, as I mentioned over here already. Right? And then the second components, I just have, 0 A1 plus 1 A2, A2 equals V2. So yes, there is a solution. I can see it right away here. And if you write this as like an augmented matrix, you have the coefficients of A1, which are 1, 0, which is just the first vector of S, right, in the first column here. And then down the next column, the coefficients of A2, which are 0, 1, which is just, the second vector in S. And this is my coefficient matrix. All right, this would be the coefficient matrix for the system. And notice that the coefficient matrix, columns of the coefficient matrix are just the vectors in S. And then on the other side, I have this, this vector from R2, V1, V2. All right, so this is the same, this little augmented matrix here is, can I write V1, V2 as a linear combination of 1, 0 and 0, 1? And then I put this in reduced row echelon form, which it has already done. Right? This is already in reduced row echelon form. and you can see that it has solutions. A1 equals V1, A2 equals V2. All right, so I could do this for every single one of these, but the V1, V2 would be messy, right? And especially if we're in R3 or R4, you'd have 3 components, 4 components, and it won't always be in reduced row echelon form. So I'll have to perform operations and mess with these variables, and it'll get really messy. So remember the shortcut for this, determining if a set of vectors spans a vector space, was just take the coefficient matrix, put the coefficient matrix that's an F, right? Put the coefficient matrix into reduced row echelon form, right? RREF, or reduced echelon form, and if that so that would just be the identity matrix here, right? 1 0 0 1, as I said, right? It's already in reduced echelon form. So I put the coefficient matrix into reduced echelon form, or reduced row echelon form, and if it has a row of entirely of zeros, if it has an entirely zero row, then S, right, the set of vectors, will not span the vector space, right? And if it doesn't, right, if not, then it will. Right, that was the little shortcut from the video I made before about determining whether a set of vectors spans a vector space. If it doesn't have an entirely zero row, then S does span the vector space in question. All right. Because again, if it has if this was 0 0, then there might be some vectors in R2 such that this element here is not 0, right? The only way you have solutions if you got 0 equals 0. But if I had 0 equals, something that wasn't 0, which would be possible, there'd be no solution. So there would definitely be some vectors in R2 that couldn't be written as a linear combination of the vectors that make up the coefficient matrix. But that's not happening here, right? This coefficient matrix has no zero rows, has all non-zero rows. Right. So that tells me that the vectors of S, right? So this set of 1 0 0 1, right, does span R2. Okay, that's wonderful. So check on number 1. Question number 1, the answer is yes. All right. So S spans R2. All right, that just means that every vector in R2 can be written as a linear combination of these two. And then the second thing we need to check is, are the vectors in S linearly independent? All right. And bear with me, for this first couple examples, I'll show you the long way first, where I do all these checks, and I'll show you. I'll describe to you a little shortcut after we get through a couple of these. All right, so question 2: is S a linearly independent set of vectors? Right? Is S linearly independent? And if the answer to this is no, then by definition, this set S would not be a basis, or not be considered a basis of R2. And if the answer to this is yes, and the first question was yes, then this is a basis of R2. All right, so remember the check for this. Remember to check for independence or dependence, you asked yourself, is there a linear combination? Take linear combinations of 1, 0, and 0, 1. So some scalar a1 times 1, 0 plus some scalar a2 times 0, 1, and say, when is that going to be equal to the 0 vector? All right, now I could also have just gone back to my equation for the span thing and just replace v1 and v2 with 0. So you're going to see that the solution is a1 equals 0, a2 equals 0. But I'll just keep going through this. All right. And this sets up a system, and the system would have this augmented matrix, right, with the coefficients of a1, the coefficients of a2, right? So there's your coefficient matrix. Again, it's just the vectors of s. And a little bar for where the equal sign is, and then the 0, 0. Okay, and then you see that from this that the value of a1 would have to be 0, and then the value of a2 would have to be 0, and that's the only solution. And this when the a1 and a2 are both 0, well, that's clearly going to give me the 0 vector. That's like the obvious solution, right? If I let all the scalars be 0, and then add them up, I'm going to get the 0 vector. So remember, this is called the trivial solution, right, wherein all the scalars are 0, and only the trivial solution is a solution of this system. And when that was the case, then the set of vectors was linearly independent. All right. If you could find a solution other than the trivial solution, then the set of vectors was dependent. And when they're dependent, right, that meant that I can write one of the vectors as a linear combination of the others. But when they're linearly independent, like these are, that means I can't write any of the vectors in the set. I can't write any of these as a linear combination of the others, or a scalar multiple of the others in this case, because there's only one other vector. All right, wonderful. So again, the answer is yes. So yes, S spans R2. Yes, S is a linearly independent set of vectors. So the instructions, determine if the set S is a basis for vector space V. It is. All right. So S equals, this set with 1, 0 and 0, 1 is a basis. It's called a basis for R2. Right. Now, this last part here, when I was checking for independence, I put the matrix in there. I didn't really mention it, but this, just like before, when I was checking for spanning, is S a spanning set of R2? And I put this in reduced row echelon form, which it already is, right? These vectors are 1, 0, 0, 1. It's already in reduced row echelon form. And again, all I'm going to really have to focus on is the coefficient matrix when determining independence, because this side of the bar with all the zeros is always going to be zeros, right? No matter what row operations you do, always going to be zeros. These won't change when you're testing for independence. So very often, you're just going to focus on the coefficient matrix and put that in reduced row echelon form. And if every column is a pivot column, right? Remember the pivots. You got the leading, where the columns where the leading ones are. And you see how every column is a pivot column. If that's the case, then you have a linearly independent set. If it's not the case, right, if there's a column that's not a pivot column, then you have linearly dependent sets. So those are the little shortcuts, right? So I wrote here, here's the shortcut for is S spanning a vector space. You make the coefficient matrix with the vectors in S, put it in reduced row echelon form. If it has a row that's entirely zero, it doesn't span V. If it doesn't have any row that's entirely zero, it does span V. So same thing here. If so to check for independence, you'll put the coefficient matrix in reduced row echelon form. Or if you set up a system and all that, you put the coefficient matrix in reduced row echelon form. All right, and then if each column is a pivot column, if every column is a pivot column, then S is linearly independent. Then you have a set of linearly independent vectors. And of course, if not every column is a pivot column, if not every column is a pivot, if not every column is a pivot column, that means you're going to have free variables and infinitely many solutions to that equation where you set up a linear combination equal to zero vector. Then S will be a set of linearly dependent vectors. Is linearly dependent as opposed to independent. All right. So I just gave you the two little shortcuts here for, especially when we're working in Euclidean space, R2, R3, R4, etc. You're just gonna, and I'll do this for the rest of them. You're just gonna make a matrix with the vectors from S as columns, right? And that would just be the coefficient matrix for a system of equations you'd be setting up to check for spanning and check for independence. And then you're just working with that coefficient matrix. Put it in reduced row echelon form, and check for, are there any rows entirely made up of zeros? Is every column a pivot column or not? Right? Just really those couple questions to determine if a set is a basis or not. Now back to earlier. You know how we said this set, right? The set with 1, 0, 0, 1. This is a basis for R2. All right, so every vector in R2 can be written as a linear combination of these two, and these two are linearly independent. Well, this is a very special set of vectors. When you make the matrix, if you put these as columns, you make the identity matrix, right? Remember, if I make the coefficient matrix is the identity matrix, right? When I have 1, 0, ones down the main diagonal, zeros everywhere else. If that's the case, you have all these vectors where there's 1 in one of the components and 0 everywhere else. This is called the standard basis for R2. Right? So this is called, with the 1, 0, and 0, 1, this is called the standard basis for R2. All right, and what you're going to notice is for R3, R4, R5, whatever, the standard basis for Rn will be made up of the columns of the n by n identity matrix. All right, and that's a big one there. All right. So they call that the standard basis for a Euclidean space R2, R3, R4, etc. All right. Okay. So that's a lot of stuff. I know I threw a lot of stuff in here, but I also have a lot of other examples. So we're going to see a lot of this definition coming back. All right. So there's a basis for R2. Great. It's got two vectors in it, 1, 0, 0, 1. Keep that in mind. So now let's look at the next example. Still working in R2. Same instructions. All right, I'm still going to be doing the same instructions as the first example. I'm asked to determine if the set S is a basis for vector space V. All right. So here, S is the set of these two vectors again. All right, 1, 1, and 1, negative 1. And the vector space is again R2, right? This is a subset of R2. Everything has two components. All right. So just to make things real quick, right? If I were to set up a system of equations involving this, where I have a linear combination of these two vectors equals a vector in R2, or a linear combination of these two vectors equals the 0 vector when I'm checking for independence, the coefficient matrix for either of those systems will simply be made up of these vectors as columns, 1, 1, 1, negative 1. All right. So what I'm going to do is take this, put it in reduced echelon form or reduced row echelon form, RREF. Now that's pretty simple here because there's only two rows. And don't forget you can do it on the calculator. I'll show you calculator stuff when we get to later examples. That's a little more complicated. If I took the opposite of row 1, added it to row 2, I'd have the 1, 0 there, and then have a negative 2 here. Then I would multiply the second row by negative 1/2 to get a 1 here, and then I could make the 0 on top of that by multiplying by negative 1 and adding it. So look at this. When I put this in reduced row echelon form, notice that there are no every row is non-zero. Every row is a non-zero row. So that means that 1, S spans R2. All right, that means that every single vector in R2, pick anything, 3, 4, 5, 7, 17, 9, whatever. Every single vector in R2 can be written as a linear combination of these two vectors. So check on that. And I'm also noticing that here's the lead one, the first lead one in this first row is right here. So the first column is a pivot column. Then the next row there's another leading one here in the second column. I'm also noting that each column contains a pivot. Right? Each column has a pivot or is a pivot column. So that tells me, number 2, the set of vectors in S are linearly independent. So that means that one of these is not a scalar multiple of the other, right? Because there's only two vectors, that's all I need to check. Is linearly independent. Great. So since both of these things are true, every vector in R2 is a linear combination of these two, and these two are linearly independent, this set S is also a basis for R2. S is a basis for R2. So just based on the first two examples, all right, we saw in the first example, this was a basis for R2, right? And it's called the standard basis because it makes the identity, it's the columns of the identity matrix. And this is also a basis for R2. So one thing to point out from these first two examples is that bases, or a basis for a vector space, I'll say a basis for a vector space, is not unique. There's not just one of them. It is not unique. All right, that's something nice to point out. Another thing to point out, and I'll make a note of this after the next example, maybe a couple more. You see how this basis has two vectors, right? This basis for R2 has two vectors. This basis for R2 also has two vectors. So what you're going to notice, hopefully in time, is that every basis for R2 will have two vectors, right? But not every set of two vectors is a basis for R2. All right, so I'm going to write that actually right now. All right, I'm going to write that note right now and then show you an example of that last statement I just said. All right, so what we're going to see here is that every basis for every basis for R2 is a set of two vectors. But, triple underline this, but not every set of two vectors is a basis for R2. Okay, so be careful. So just because you see a set of two vectors, just because those first two examples were bases of R2, doesn't mean that every set of two vectors is a basis for R2. So let's see that in this, well, not this next example. Let's, well, I'll just do the next two and we'll see. I mean, this one is another basis, but let me just show you. Okay. So I'll bring this statement back. All right. So here I see a set of two vectors, and again I'm asking, is this set of vectors a basis for R2? All right, so can every vector in R2 be written as a linear combination of these two? And, so that means does S span R2? And are these two vectors linearly independent? Okay. So again, when you set up that system of equations, when you set up a linear combination of these two equals any vector in R2, and when you're checking for independence, you're setting up the equation, a linear combination of these two equals the zero vector. In either case, the coefficient matrix for that system is the following. Just a 2 by 2 where, again, these vectors are the columns of the coefficient matrix when you set up those systems. All right, and I'm going to put this in reduced row echelon form. All right, now I'm already seeing that these are independent, right? These are not scalar multiples of each other. Now I'm going to just to So the reduced row echelon form is going to be the identity matrix, but let me show you on the calculator as well. I'm just going to save some time in writing here. So if you go to the calculator, and this is an 84 plus silver edition, it's like the 83 as well if you have a TI 83. Go to the matrix menu above X inverse here, go over to edit, and this is a 2 by 2 matrix, right? Enter the size first, 2 rows, two rows, right? 2 columns. And the first row is 4, 5. I just make these entries. The second row is -3, 2. Make these entries. Get out of here, and then I want to put this in what's called again reduced echelon form or reduced row echelon form. RREF is what you're going to see on the calculator. So I go to the matrix menu again, over to math, scroll until you get to B, up or down until you get to this RREF. Don't confuse it with REF. That's row echelon form, just plain old echelon form. All right. I want RREF, and then what matrix do I want to put in that form? Matrix A, right? The 2 by 2 under the names. And you see it's the identity matrix, right? As I said it was going to be, so 1, 0. And again, you can do this by hand with row operations and whatnot. All right, so again, I look at the coefficient matrix in reduced row echelon form in very simple checks. One is I notice when I look at the rows, all the rows are non-zero. All right, and there's no row made up of entirely of zeros. So that tells me that, one, this set of vectors spans R2. So good on that. And then looking at the columns, which columns have pivots, which columns have these leading ones. Well, the first column has the leading one from row 1, and the second column has the leading one from row 2. So all columns have a pivot. Real shortcut here to indicate to me that yes, indeed, these vectors are linearly independent. All right. So 2, S is linearly independent. Check. So both of these things are happening. So yet again, I have the fact that S, well, that's getting pretty faint. This set of vectors is a basis for R2. Wonderful. All right, so again, the fact comes up that a basis for a vector space is not unique. I've already shown you 3 different bases for R2. This set and this set, right, the standard basis with the columns of the identity matrix, and this set with 1, 1, and 1, -1. All right, now finally to the point I made here. So every basis of R2 is going to be a set of 2 vectors, as you've seen, right? Every basis had 2 vectors. But not every set of 2 vectors will be a basis for R2. All right, and let me show you that with this example here. So here's a set with 2 vectors from R2, and I'm asking again the same question: is this set of vectors a basis for R2? Right? So can every vector in R2 be written as a linear combination of these two? And are these 2 vectors linearly independent? Now hopefully you can see that they're not independent because they're scalar multiples of each other. I can just multiply this vector by 3 and get this vector. All right, so they're definitely dependent vectors. But again, I'll go through the shortcut thing, what I'm going to do for every single one of these examples. All right, if I were to, I thought I saw that was faint. I'm going to pitch that one. All right, so if I were to set up the equations that I was for this, checking for does S span R2, and is S linearly independent, where I would take a linear combination of these two and set it equal to any vector in R2, And then to check for independence, I take a linear combination of these two and set it equal to the 0 vector. In both of those cases, the coefficient matrix for the system would be, with these columns 2, 3, 6, 9. And then I want to put this through Gauss-Jordan elimination or using the calculator into reduced row echelon form or reduced echelon form. Now this one's an easy one because you see if I just multiply the top row by -3/2 and add it to the bottom row will be entirely of zeros. And then I multiply the top row by 1/2 and I get my leading 1, 1, 3. And there you go. And you can double check on the calculator if you want. But this will be the reduced row echelon form. So, one thing I'm noticing, there is a row of zeros. There is a 0 row. So that tells me that S does not span R2. Okay. Now, that's all I mean. I can just stop there. All right. S does not span R2, and it has to satisfy both properties to be considered a basis for the vector space. It has to span it and be a linearly independent set. So this means that there's some vectors out there. There's at least one vector in R2 that is not a linear combination of these two vectors. Now, I don't have to find him. Right? You can if you want, but that's bad, right? And and again, I can stop here and jump to the conclusion that S is not a basis for R2. But I'm going to point out one other thing as well. Look at the pivots, right? There's a lead 1 in this first column, and then this row doesn't have any leading 1s, right? It's a row of entirely zeros, so only one column. So not all the columns have a pivot, have one of those leading 1s. So that also leads me to the conclusion that S is not linearly independent, right? Or it's linearly dependent, right? But it's not linearly independent. And independent. So that's bad too, right? Again, both don't have to fail. If one of them fails, then it's not a basis. Right? And again, if I say S is not linearly independent, that just means it's dependent, meaning that one of the vectors can be written as a linear combination of the other ones. And as I said earlier, 6, 9 is just 3 times this first vector, right? So definitely here we have S is not a basis for R2. Right. So this, like I said earlier, just because you see, the first 3 examples I gave were sets of 2 vectors and they were bases for R2, just because you see a set of 2 vectors does not mean you have a basis for R2. Right. Okay. So now comes the simpler examples from R2 anyway, and then we'll go to R3. All right. So here's S equals, this setup with one vector from R2, one vector only, -3, 2 there. And I'm asking, is S a basis for R2, right? Can I write R2 as, if I take any vector in R2, is it a scalar multiple or a linear combination of this vector? Well, no, clearly not, right? Also, is this vector linearly independent? Well, yeah, a set with one vector is independent if it's a non-zero vector like this is. Now, I know this sounds silly, but you could do this as well. The thing I've been doing where if I were to set, a scalar multiple of this equal to any vector in R2 and a scalar multiple of this equal to the 0 vector to test for independence, the coefficient matrix in either one of those would be this 2 by 1 matrix here. All right, and then I go to put this in reduced row echelon form. Right, that I would multiply the top row by negative 1/3 to get it to be a 1. And remember, every leading one, every pivot has zeros below it and above it, but there's nothing above it. So just zeros below it. I would multiply that top row now by negative 2 and then add it to the bottom row. Again, very silly. This, you can tell right away that it's not a basis, and I'll explain why in a second. But then looking at the reduced row echelon form, I notice there is a row of zeros. Right, this second row is made up entirely of zeros. There is a 0 row, so S, this set of vectors, does not span R2. And that's bad. And then, so right away you can say that S is not a basis for R2. And then looking at the columns, now the pivots are the leading ones in any of the rows when you're in reduced row echelon form or echelon form. The only pivot is this thing, right? This is the leading one in the first row, and it's in the only column. So every column does have a pivot, right? The only column there is has a pivot. So this set of vectors is linearly independent, right? S is linearly independent. But it doesn't matter, right? It doesn't matter if it's linearly independent. It does not span, the set does not span R2. There are vectors in R2 that can't be written as a scalar multiple of negative 3, 2. So S is not a basis for R2. Now, a much easier way to determine this, again, I didn't have to do the whole reduced row echelon form. I can always do it, all right? That's not a problem. Just remember earlier I said every basis for R2 is going to have 2 vectors in it, and 2 vectors only. This does not have 2 vectors in it, so it couldn't be a basis. I'm done. All right, you can very simply say that if you already know that fact. All right, and the same thing is going to go for R3 and R4 and all the way up to R whatever, any Euclidean space. And I'll write that note later when we get to R3. All right, but you're going to see every basis of R3 is going to have 3 vectors in it. Every basis of R4 is going to have 4 vectors in it, and so on. All right, so now the next example, and I think it's my last one from R2, and then we'll move into R3. I have a set of vectors, right? S equals these 3 vectors from R2. 1, 2, 1, 0, 0, 1. And then again, the vector space is R2. Okay, so the question is again, does S form a basis for R2? Now, already I can tell you it doesn't. Right? Remember, I mentioned earlier, every basis of R2 should have 2 vectors in it. This has 3, so it can't be a basis, right? But let's, I'm going to do the same thing I've been doing. If you were to set up those equations, right? If you were to set up take a linear combination of these 3 vectors equal to any vector, v1, v2 in R2, or if you were to check for independence, right? Take a linear combination of these vectors and set it equal to the 0 vector. The coefficient matrix would be this 1, 2, 1, 0, 0, 1 for all of those. All right, and then I'm going to say, let's put this in reduced row echelon form or reduced echelon form. Okay, again, this one's not so bad. There's a lead 1. I would multiply this first row by, negative 2. Add it to that second row to get me a 0 below it. And then that would put, negative 2 here, which I could then multiply the second row by a negative half to give me a 1 here, and then I would be able to clear the 0 above it. And then this I would have, I would add, sorry, I might put this in the calculator, check it out. I confused myself already. So I'd have negative 2 down here, I multiply it by a half, and then, okay, so might have a little messy. All right, I'm sorry, I'm confusing myself. But I should be able to put this in. I normally do this by hand, one step at a time. I apologize. So if we go to the calculator matrix, set up a little 2x3 matrix here. First row 1 1 0. Second row 2 0 1. And then let's get out of here. And the last entry I put in was the reduce echelon form already, so I can just re-enter that by going second and then entry. And yeah, you get halves, right? That's probably why it messed me up. I don't know why I didn't see that. Sorry. So the up here 1/2, down here -1/2, right? Okay, so if you look at these, right, look at the rows. There aren't any 0 rows, right? All rows are non-zero. All rows are non-zero rows, telling me that this set does span R2. Right, so 1S does span. S spans R2, meaning that every vector in R2 is can be written as a linear combination of these three. All right. And then you look at the pivots, right? The leading one, what columns the leading ones are in. That one there, and in the second column. But the third column is not a pivot column. The third column does not contain a pivot, so not every column contains a pivot. And that tells me that this set of vectors is not linearly independent. And you might have also been able to tell that there was again, if you've been watching my videos, I put a video up on checking for independence. If the number of vectors is greater than the number of components in each vector, then the set's going to be dependent, not independent. Right? So S is linearly dependent. Right? Linearly dependent, not independent. All right, and that's bad. All right, I don't want that. This is good, but as long as one of them fails, we're not a basis. Right? So S is not a basis for R2. And like I said at the beginning of this example, you can very easily say that because there aren't two vectors in it. All right, every basis of R2 has to have two vectors in it. But be careful though. Right? You saw an example earlier. Just because a set has two vectors doesn't mean it's going to be a basis. So if I'm giving you a set of two vectors, you actually have to go and check. All right. But if I give you a set of 3 vectors, not a basis, for R2 anyway. A set of 1 vector, not a basis. A set with 5 vectors for R2, not a basis. Right? Hopefully that's clear. All right. Now my last examples, right? Not my last example, but my last examples, plenty, are from R3. Now you might recognize this guy. Right? I'm asking, is this set of vectors a basis for R3? Right? So can every vector in R3 be written as a linear combination of these? And are these 3 linearly independent? This is that standard basis. Right? Remember when if I were to form, see all these columns here, if you put them into a matrix, would make the 3x3 identity matrix. Right? Remember, if the columns of the identity matrix are my vectors, then we have what's called a standard basis for the Euclidean space. Okay, but I'll do the same. Right? The coefficient matrix, if I were to take a linear combination of these, set it equal to any vector from R3, maybe V1, V2, V3, and then I test, to check for spanning. And then if I was testing for independence, I'd take a linear combination of these vectors, set it equal to the 0 vector, 0, 0, 0. And in either case, the coefficient matrix would be this, 1, 0, 0, 0, 1, 0, 0, 0, 1. The identity matrix, and it's already in reduced row echelon form. And if you look at the rows, there are, all rows are non-zero. So these vectors do span R3. So I'm going to stop writing 1 and 2. Right? S spans R3, right? Every vector in R3 can be written as a linear combination of these 3 vectors. Check. And then looking at the columns in reduced echelon form, every column has a pivot, has one of these leading ones in the rows. So every column has a pivot. Telling me that these vectors are independent. You can't take one of them and write as a linear combination of the others. All right. So S is linearly independent, and that's wonderful. All right. Both things hold. So S is a basis, and in fact, they say because these columns are from the identity matrix for the 3x3 identity matrix, S is the standard basis for R3. All right, wonderful. So look at this. This basis for R3 has 3 vectors in it. Right? All the bases for R2 had 2 vectors in it. And the first basis I come across for R3 has 3 vectors in it. And what you're going to notice, through other practice and through examples you're going to see from me here, is that every basis of R3 will have 3 vectors in it. But, right, just like in R2, not every set of 3 vectors will be a basis for R3. And I'm going to write this in general, right, for Rn. Okay. So this is a really general statement right here. So in general, right, for Rn, right, so R2, R3, R4, R5, etc. Every basis of Rn, okay, the n-dimensional Euclidean space, is a set of n vectors. But not every set of n vectors is a basis of Rn. That is huge, okay? So just because, if I'm in R3, just because I give you a set of 3 vectors, that does not mean that that is a basis. You have to check it. Okay, but if I give you a set of 4 vectors from R3, you can tell me right away it's not going to be a basis. If I give you a set of 2 vectors or 1 vector from R3, you can tell me right away it's not going to be a basis. All right, but again, if it has 3 vectors from R3, you have to check. Right? You can't just say it's going to be a basis. You don't really know that right away. All right, so be careful. Okay, so here we go. Another set of vectors from R3. All right, so the set of again, it's a set of 3. It's got 3 vectors. So it might be a basis for R3, but I don't know for certain. You cannot say for certain. So I have to check So again, if I were to set up the linear combination of these equals any vector from R3, or in checking for independence, I'd set linear combinations of these equal to the 0 vector. In either case, the coefficient matrix would be this matrix here, with the columns being these vectors. Alrighty, and then I'll put this into reduced row echelon form. Now, if you were to set this equal to something, you see how the first line says that the first A1 would be equal to something, and you pop that here and then solve for A2, and then you would pop those here and solve for A3. So there would be like one specific solution to the systems that you set up. You know, you could solve through like forward substitution, I guess you could call it, from top to bottom. So I can tell right now that the identity matrix, you know, 1 0 0 0 1 0 0 0 1 is going to be this matrix put into reduced row echelon form. Now, if you'd like to double check, right, let me just verify this with the calculator. Second matrix, make it a 3 by 3 matrix now. Where I have 1 0 0, and then 5 1 0, and then 3 2 6 for the third row. Alright, and then get out of here and re-enter the reduced row echelon form statement. And you see it's the identity matrix, like I said. Alright, so I'm just going to jump to it. Alright, I'm not going to write them anymore. I've done it a bunch. There are no all 0 rows, so S spans R3. Good. Every vector in R3 can be written as a linear combination of these three. And every column has a pivot. Every column has one of those leading ones. So S is linearly independent. Right, that means that any of these vectors, you know, pick a vector, cannot be written as a linear combination of the other two. Right. And since both of these hold, S is a, you know, basis, a non-standard basis, right? You know, I showed you what a standard basis was. Any other basis will be a non-standard basis, but I'm not going to write that. Right? S is a basis for R3. All right, and then this takes me back to that statement, you know, bases for a vector space are not unique, right? You know, the standard basis on the previous example was a basis for R3. This is a basis for R3. And again, just notice that they have 3 vectors. All right. So every basis for R3 is going to have 3 vectors in it, but not every set of 3 vectors will be a basis for R3. I hope that's very clear. All right, so next example. Got another set of 3 vectors. So again, the question is S a basis for R3? So is every vector of R3 a linear combination of these 3? And are these 3 independent? So one more time here. If I were to set up the equations, you know, linear combination of these 3 equals any vector, you know, v1, v2, v3 in R3, to check for spanning, and then to check for independence, I, you know, take this linear combination of these vectors, set it equal to the 0 vector, try to find solutions to that. In either one of those systems, you have the coefficient matrix where, you know, these columns are the columns of the matrix. These vectors are the columns of the matrix. Okay. And then I would put these, you know, through either by hand with row operations, Gauss-Jordan elimination, or through the calculator, which I'm going to do here. Put this in reduced echelon form, reduced row echelon form. All right, so here to the matrix menu. This is another 3 by 3. All right, so keep the size. The first row 0, 4, -8. Second row 3, 0, 15, third row, -2, 3, -16. Okay, and get out of here, and I've already entered the reduced row echelon form, so let's just re-enter it. Alright, so here it is in reduced row echelon form. 1, 0, 0, 0, 1, 0, 5, -2, 0. Alright, so again, I'm not going to write out the stuff anymore. I've written it out enough. Look at the rows. There is a row made up entirely of zeros. So S does not span R3. And that's bad. All right. So right away I can say that this set of 3 vectors is not a basis for R3. Remember I said that, right? Not every set of 3 vectors will be a basis for R3. So that means that there are some vectors in R3 that can't be written as a linear combination of these 3 vectors. And then if you look at the pivots, right, there's a pivot in the first column, pivot in the second column, those leading ones. But there's not a pivot in the third column. So not every column has a pivot. So not only does S not span R3, but these vectors aren't even linearly independent. S is linearly dependent, right? Not independent. And that's bad too, right? If I'm talking about bases. And what that means is that, I could pick one of these I could write one of these vectors as a linear combination of the other two. Right? One of those depends on the others. So we definitely have the case here where S is not a basis for R3. Okay. All right, and then I have these. I have just 2 more examples, but these are very, very simple. All right. I've already talked about, the general statement about Rn. Remember, every basis of Rn has n vectors. But, not every set of n vectors is a basis for Rn. Well, noting that here's a set of vectors. S says, there are 2 vectors from R3, right, with 3 components. And I'm asking, is S a basis for R3? No. Right? Every basis for R3 will have 3 vectors. Exactly 3 vectors. I should say exactly 3 vectors. All right. This does not have 3 vectors in it from R3. So S is not a basis. Now I could do the same thing I've been doing. Right, is not a basis for R3. Right, that's good. All right. But I could do the same thing I've been doing, where if I were to set up those equations I've mentioned to check for spanning and check for independence, I'd have this coefficient matrix. And then I go to put this in reduced row echelon form. Let's see what we get. All right, again, that's it's not that hard to do. Now let me show you. If I don't know if I've pointed this out in another video, but you're going to see a little error pop up here. Let me show you. I go to make a matrix, and this is a 3x2 matrix now. So 3x2, and then the first row has entries 2, 0. The second row has 1, -1. The third row has 0, 1. Okay, I get out of here, and look at what happens when I go to put this in reduced row echelon form. Uh-oh. Now, I don't know why this happens. I mean, you could do this by hand. It wouldn't be too terribly difficult. But if you want to have the calculator do something, when there are more rows than columns, it's going to come up with an error saying invalid dimensions on your calculator. This is a very simple fix. Go back to the matrix menu and go to this matrix where there are more rows than columns, and just increase the number of columns so that you have an equal number of rows or even more columns than rows. But just go make it a 3 by 3. You see what happens? It just adds on columns of zeros. And then I can go back and do reduce row echelon form and just ignore the columns of zeros, right? Because when you do row operations, any column of zeros is going to stay as a column of zeros. I think I've mentioned that before, even in this video. So I add these columns of zeros so that the number of rows and columns are equal now. And then I can do reduce row echelon form again, and it'll do it. And again, just ignore the columns of zeros that were added. This was a 3 by 2 matrix, so just enter that 3 by 2 matrix here on the left side of this. All right, so in reduce row echelon form, this is 1 0 0 1 0 0 0 1 0, and that's it, right? Just ignore that third column of zeros that got added. All right, and notice when I look at this, oh, there's a row made up entirely of zeros, so S does not span R3, and that's bad. All right, so definitely S is not a basis for R3. But the pivots, there's a pivot in column 1, there's a pivot in column 2, right? These leading ones. So every column has a pivot. So S is linearly independent, right? I mean, there's only 2 vectors. You just need to check to see if they're scalar multiples, which they aren't. So these are linearly independent. Okay, that's fine. But again, as long as one of them fails, it fails to be a basis. Right? And like I said earlier, you don't even need to do all this if you recognize, hey, there's not enough vectors. Every basis for R3 has got to have exactly 3 vectors in it. In R4, the bases have to have 4 vectors and so on. All right, and then one final example, and I'm just going to do it really quick. I'm not even going to put the matrix in. All right. Is S this set of 4 vectors from R3? Is S a basis for R3? No, it can't be. All right, and I think I mentioned this earlier too. This is going to be a dependent set, right? The number of vectors is more than the number of components in each vector. So this is not going to be an independent set. I can tell you that right now. But it doesn't have 3 vectors in it, and we're talking R3. So I'm just going to jump to S is not a basis for R3. It can't be. All right. The only ones you're really going to need to check are the ones with the correct, the sets with the correct numbers of vectors, right? Only in R3, when you have a set of 3 vectors, that's going to be the only time you're really going to need to check, is it a basis or not? In R4, set of 4 vectors, you have to check. R5, set of 5 vectors, you have to check. All right, so again, it's pretty simple, I feel. So there's a lot of putting some coefficient matrices in systems, putting those coefficient matrices into reduced row echelon form, and looking for, are there any rows made up entirely of zeros? If there are, the set doesn't span the vector space. If there aren't, the set does span the vector space, and that's great. And then you look at the columns where all the leading ones of the rows are. You look at the columns where are the pivots. If all the columns have pivots, wonderful. That means the set is linearly independent. All right. And if not all the columns have pivots, that means that the set is linearly dependent, right? And therefore the set would not be a basis for the vector space. All right. So lots of stuff to mull over there, lots of examples to look through. You don't have to watch them all. If you got the gist of it after the first few, hopefully you haven't watched this far. If you understood what was going on after the first few, but, just have fun practicing this kind of stuff on your own. And thank you very much for watching.